Section 12.4 talks about the cross product. The formula given normally is if A is given by A sub 1, A sub 2, A sub 3, and vector B is given by B sub 1, B sub 2, B sub 3, that would be the cross product. Kind of hard to remember. So if I want to take A cross B, this is what we're going to do, and we're going to be doing that for some time. We're going to find the determinant, and you list them in order. It's important for you to go in order. B after, and A cross B would be simply, and this is how it works. If you take the I component, so I'm gonna color code those. The I component, remember how this works. Associated with each, yeah, I'll put them right here. Associated with each matrix is cofactors. Now we're gonna always use the first row in this class, so no need to worry about the rest of the signs. They really don't matter. I take the I component. Now I cross everything in I's row and column. What's left is 2 by 2. A sub 2, B sub 3 minus A sub 3, B sub 2. The J component always take a negative. And now, that's why I drew those really long, so I can cross them out. If I look at the B component, the J component, I cross its row and column. Well, what's left is A1, B3 minus A3, B1. The determinant of a 2 by 2. And again, if I take that out now, and if I look at the K component, cross K's row and column, I'm left with A sub 1, B sub 2 minus A sub 2, B sub 1. And you'll notice if you distribute the negative into the J component, you will pretty much get exactly that vector. And that's really what it is. So it's not simple to memorize that. It's much easier to do this, something you're going to have to do, and you'll start playing with this faster as we do them over and over. Now, we have a theorem. The vector A cross B. So A cross B is a vector. A dot B is a scalar. A cross B is a vector. It has the I component, the J component, and the K component. If I take A cross B, that would be orthogonal to both vectors A and vector B, and we're going to verify that in the next example. I'm looking at example 1, part A. It says find A cross B and B cross A, and verify that A cross B is orthogonal to both A and B. Well, example A, if I want to find A cross B, what I want, I, J, K, I'm going to list A first and B after, in that order. And that's going to be the I component. It's going to be negative 9 minus 36. The J component, negative, always a negative because of the cofactors. If I really eliminate J's row and column, that's 9 minus 20. And if I look at the K component, 27 minus a negative 15 will be plus 15. I just made these numbers up, so they might not appear to be that nice, but that's okay, we could handle that. So I'm getting A cross B to be a vector, and that vector is negative 45. This is negative 11 times a negative, that's positive 11, and a 42 if I'm not mistaken. Alright, now if I take B cross A, what would that be? Well, I have to do it again. I, J, K. I'm going to move part B to the bottom in a minute. I'm going to list B first, A after, in that specific order. And what that's going to be, that's going to give me the I component again, 36 minus a negative 9 is plus 9. The J component, negative 20 minus 9 and of course the K component, that would be negative 15 minus 27. And what do I notice? I notice that B cross A is actually 45. This is 11, negative 11, and negative 42. So, do we see the correlation between those? It turns out A cross B equals negative B cross A. Something to always keep in mind. Now, verify that A cross B is orthogonal to A and B. Again, I'm going to take this out. I'll work that out right underneath. And I only want to show you something out of this example, really. So how does that work? If I take A cross B, dot it with vector A, what am I looking for? I'm looking if I'm going to get a 0. I'm looking at negative 45, 11, and 42. That's A cross B. Dot it with A. And A happened to be 3, negative 3, and 4. That would be a scalar. That's negative, what is that? 135 minus 33 plus 168, not 2, 68. So that is negative an 8, negative 168 plus 168, which is 0. And of course, if I take A cross B dotted with B, I will get a 0 as well. Hopefully you're going to take my word for it. Why would I lie? And if I looked at example B, now if I have 2 dimensions, I could really do the A cross B still. This is all what I have to do. I have to add the K component, which is 0. When I find A cross B, I will simply write I, J, K. The A first, 1, negative 2. Since there's no K component, I'll just put a 0 for it. And the same thing with B. And that's really how you get around this. I mean, it's going to be quick and simpler. If I cross the I, now you could start covering with your finger the I column, and it's simply 0 minus 0, meaning if I am to cover A, I, 0 minus 0 is 0. That's not that challenging. Again, you could cover with your finger the J component and just do the product across, or simply in the beginning 0 minus 0 is also 0. That doesn't look that bad. And how about the K component? The K component will be 2 minus a negative 2. 2 minus 6, which is 8. So hopefully I didn't make a mistake. 2, yep, I don't make mistakes. That's a joke. So I got, in this case, A cross B to equal 0, 0, 8. Now, I know automatically from the previous problem, B cross A is going to be negative, the opposite of that. And I could take A cross B and dot that with A. That is, and any time throughout this class, you're given 2 dimensions of a vector, you could make it 3 by adding the 0 for the missing component. And I notice that's 0 plus 0 plus 0, which is 0. Very simple to show. I did want to point out, I could take A cross B and write that as 8 times 0, 0, 1. Remember, this is the length. And what do we call this? Direction. Something that we need to really come back to every now and then and keep that in mind. Now, the direction of A cross B, it's very important. There's a right-hand rule. It says if A and B share a common vertex, and the angle between them is between 0 and 180, line up your right hand with vector A, the vector that comes in first, and curl your fingers toward vector B. Your thumb is the direction of A cross B. So here they're asking for a few things. They're asking for A, find A cross B, and B, sketch all of these 3 vectors. Well, let's do A cross B. Again, it's a good practice. That is I, J, and K, 3, 3, 0, 0, 2, 0. Again, that's going to be, if I cross the I, it's 0 minus 0, which is 0. If I cross the J, it's going to be 0 minus 0, which is also 0. Yeah, I picked it that way. And if I look at the K, it's going to be 6 minus 0, which is just 6. So, if I get my grid, and I sketch vector A, which is 3, 3. There's vector A. If I look at vector B happened to be 0, 2. There's vector B. Now, if I line up my hand with the blue, which is on the floor, and I curl my fingers toward B, I should expect the direction to be somewhere along that path. Why is that? Well, it has to be perpendicular to both. And if I look at what I got, okay, I messed up big time. You guys forgive me, right? I plotted B fully wrong. A was fine. Vector B was, you guys weren't going to say anything. 0, 2. It's right there. I made it 0, 0, 2 by mistake, right? Okay. If I curl my hand, if I line up my right hand on A and curl my fingers toward B, do you agree that this is the direction that's going to be perpendicular to both? Well, 0, 0, 6 is A cross B. Do we agree that this vector right here is perpendicular to both A and B? So if vector A and vector B happen to be on the floor, the perpendicular to the floor is going straight up. We call that normal. Alright, a formula that works out, something that we need to get out of the cross product. If theta is the angle between two vectors A and B sharing a common vertex, then A cross B is the magnitude of A times the magnitude of B times the sine of theta. This formula we don't use that much really. Unlike the dot product. The dot product we use a lot. A dot B equal vector A dot vector B is the magnitude of A, magnitude of B times, if you recall, right there. That we use a lot more. But this one we really don't use much, but it's good to know. But what we get out of it? Well, if theta is 0 or pi, then the cross product is 0. And if the cross product is 0, that means to us now that A and B are parallel, because if you have two vectors share a common vertex, if the angle between them is 0, they line up, and if the angle between them is pi, they point in opposite direction, which indicates they are parallel. Now something that we really need to get out of the way, this we are gonna use a lot, and it's very useful. Given vectors A and B, if I sketch a graph of A, let me make that's fine. And if I sketch vector B, so let's say this is A and let's say this is B. If I would like to find the area of the triangle that this encloses, if I would like to find, if I would like to find this area, I would say, assuming there's the angle theta, I would say area of the triangle is 1/2 base times height. Area of the triangle is going to be 1/2. Now, if I look at, I should have drawn it slightly different. That's okay. That's the height. If that's the height, then this is the base. So this is going to be 1/2. The magnitude of B would be the base. Now, the height. To find the height, I would say, well, look, the sine of theta is the opposite over the hypotenuse. Or simply, the height is the magnitude of A times the sine of theta. And if I look closely, the magnitude of A times the sine of theta is right there. Wouldn't that be vector A cross B divided by the magnitude of B? Actually, I messed up slightly, I apologize. This is really the magnitude of the cross product. And what do you notice? Those cancel out. So what do I get out of this? I'll get the area of the triangle is 1/2 the cross product. Or even better, if I really want to get it out of the way, an easier way to remember, if you find the cross product of two vectors, if you take the magnitude of that, so the magnitude of the cross product is the area of the parallelogram that the two vectors enclose. And hence, every time you want to find the area of the triangle, it's 1/2 the cross product. So, last example I have, two more. This and one more. The last one is a bonus. I know you like those. Given 3 points, 1, 1, 2, again, graphing those is really not the point. but you'll notice in 3D it's kind of hard to visualize unless you're doing the graphing. 1, 1, 1, 2, that's 1 point, that's A. -2, 3, 0, and 0, 4, 2. So again, a bit hard to visualize, but there it is. If I want to find the area of this triangle, how do I do that? Well, a couple of options. Here, those happen to be at the same height, but this is what I could do. I could find vector AB, that is -3, -3 minus 1 is 2, and 0 minus 2 is -2. And I could find vector AC to make sure that they share a common vertex. Now, it doesn't matter which two vectors you find. You could have found BA, BC, or CB, CA. It makes no difference, but as long as they share a common vertex, that would be 0 minus 1, 4 minus 1, and 2 minus 2. And if I take the IJK, again, it would be wise to start doing that. You could just run it right there. The I component, 0 minus a -6 is 6. After you do this enough times, you start picking up those quick cuts. And if I cut the J off, that's 0 minus a 2. Again, you could probably start doing that in your head in the long run. And the K component, you're really going to take -9 plus 2. If I didn't make a mistake, that would be the cross product. That's AB crossed with AC. That is 6, 2, -7. Hopefully I didn't make a mistake. Now, if I take the magnitude of AB crossed with AC, that is the square root of 36 plus 4 plus 49. And that would be the square root of, what is that, 89. So area of the triangle ABC is actually square root of 89 divided by 2. And there it is. Now, part B is something that keeps on coming back over and over. Find two unit vectors perpendicular to the plane. Now, remember, I could take vector A cross B, AB crossed with AC. Since the length is 89, I could say that's the square root of 89, if you recall, and say that's 6 over radical 89, 2 over radical 89, and -7 over radical 89. This would be the length, and this would be the direction. And since they want find two unit vectors perpendicular to the plane, well, what would that be? Well, AB, but a unit vector, and AC, remember, the cross product is orthogonal to both vectors that you used. Well, what's a unit vector? It's right there. 6 over radical 89, 2 over radical 89, and -7 over radical 89. But they said find 2. Well, plus or minus, of course. That's always the case. And if I look at the last example, again, I'm repeating the same thing. Given vectors A and B, find two unit vectors that are orthogonal to A and B. I'm going to go ahead and really quick find A cross B. I, J, K, 1, -4, 2, 0, 3, 1. That would be the I component. 4 minus 6 is a -2. The J component is 1 minus 0, done. And the K component, 3 minus 4. And really quick, that's a vector. If I write this vector like they want me to always, if I find the magnitude of that vector, that's the square root of 4 plus 1 plus 9, that's radical 14. So, the author is going to ask a lot for the length. I could say A cross B is radical 14 times -2 over radical 14, -1 over radical 14, and 3 over radical 14. This is the length. And this is the direction. What's so special about the direction? In this book, they like the direction to be a unit, and we talked about that in the previous sections. Find two unit vectors, well, plus or minus -2 over radical 14, -1 over radical 14, and 3 over radical 14. And that's pretty much what this section is all about.